So in this video I would like to talk about the effect of line inductance. So if you remember, basically we ignored that inductance in our first calculations, but in a reality case we have the grid voltage, but that grid voltage is coming to your source with some cables or that kind of transformers, so you always have some inductance. Again, this is not a separate inductance that you connect. That is the inductance that you have due to connection of the cables, transformer, transmission lines, that kind of system. So that is a component that you cannot get rid of. So the problem is, once we have not the ideal voltage source but connected through an inductance, you want to, in this case, you still have the ideal current source here, and if you remember it from the previous lecture, the source voltage will be a square waveform. So IS should be like square waveform. But the problem is, if you have a sharp edges like that, that inductance value, it is the inductance current is the same as the source current, VL is equal L di over dt, and because of that sharp edge, basically VL will go to infinite. Okay, that is not possible, and it will destroy all our semiconductors and other cables, and actually it will not open at all like that. So what kind of waveform does that system draw? So basically it will not be a perfect current waveform anymore, but it has to be modified. So before going on to that one, so let's start with a simple circuit. So this is not a full bridge rectifier, but you have just two diodes. We still have the ideal current source here, so it will draw the current either D1 or D2. And let's say at t smaller than 0, so let's say Vs is smaller than 0, so D1 is off, so D2 is on. So basically at the initial condition we have all the current flowing through here, and our D1 is off. So let me draw it like that. So all the current is flowing like that. So what will happen if we reach to t is now getting bigger and our voltage source is getting larger? Okay, so this is those things. So now this inductor would like to get in, and that inductor would like to go out. But again, the problem is, if we do it instantaneously, if this happens instantaneously, from the inductor's point of view, it was carrying D1 is 0, D1 is off, so it was carrying no current, and after t larger than 0, now D1 is on, so it will make a sharp rise, and again VL will go to infinite. So of course this will not happen, so let's try to think how we can model that thing. So take that one. So at that instant our diode is forward biased, right? Because whenever that one is conducting, that voltage was 0 volts. Now that one is larger than 0 volts, and that diode is forward in conduction mode. So basically now it is on. So let me show it with an yellow arrow, green arrow. So the problem is that from the inductor's point of view, what we'll see is VL is equal L di over dt, and since Vs is not infinite, there will be some time to increase the current. So if you think about it, let me draw it here. Let's say this is IL, and hence it is the same with ID1. So it was 0 at that point, and with that voltage difference, it will start increasing, and that thing is increasing with the sinusoidal. So basically, if you take the derivative, it will be another waveform. So it will start increasing, right? Then from that current source point of view, let's say this is 10 amps, okay, and if that diode current has reached to 1 amp, again this is an ideal current source, and it will have the 9 amps from here. So from the other diode's perspective, so this is let's say D1, this is D2, and it was starting with 10 amp. Just at the instant it was carrying 10 amps ideally. Now it will start going down, and at that instant, whenever for example, if this is 1 amps, this is 9 amps. So as that voltage gets bigger, Vs is increasing at the positive cycle, so does the L di over dt term. So basically the derivative of the I is keep increasing. So let me redraw that part. So it will be going like that, okay, and basically that one is going like that. We will calculate the waveforms, don't worry about that one for now. And what will happen at that instant? At that instant, after some time, this will reach to 10 amps, and once D1 voltage is now 10 amp, okay, and that D2 voltage will reach to 0 amp, okay, so it will reach to 0 amp. And after that point, of course, the D2 cannot go to negative, so D2 is off, and this will stay constant at 10 amps, and all that region will be where D1 is on. And interestingly, during that time, D2 is on. So basically it starts with one of the diodes, and then the other one helps him to get the 10 amps. So for some period of time, and we call that time the commutation period. So for commutation period, so let's call this area like T1. So for T smaller than T1 and larger than 0, we have D1 is on and D2 is on. So during the commutation period, it's also called the overlapping period. So this is either called commutation or overlapping period. So we have both the D1 and D2 are on, and actually the current on the grid size doesn't make a sharp rise, but it just rise slowly. I mean, again, it is like in the order of milliseconds, but again now the L di dt term is limited, so during that time D1 and D2 are in conduction. So let me draw the output voltage. So in this case, so if D1 and D2, let me show it with green to be consistent. So if D1 is on and if D2 is on as well. So what is our VD voltage? I mean, if this is 0 volts and this is in conduction, so basically VD will be 0. So let me try to plot the function of time. So during commutation time, my output voltage will be 0, and as soon as that diode gets out of the conduction, right? If that diode is now off, okay, so now all that waveform is now being transferred by the VL, and now our current is constant, ID is constant, so VL is equal L di over dt. Again, it will not happen if you just connect the resistive load. We have an ideal current source, so in this case VL will be 0, and if VL is 0, VD will be equal to VS. So this will be like carrying DC current, no voltage drop, so VS will be transferred to VD. So you will have a output voltage, maybe I'm exaggerating the commutation time, but you will have an output voltage like that, right? So now at that instant we will have the same thing. So this is VD voltage, and that value is, if this is the RMS value, this is square root to Vs. So if it were just the same circuit without no inductance, I will have that dash line, but now I have a delayed response, because if D2 is in conduction, I see 0 voltage at the output. What about after that time? So after that time, let me clean a little bit. So after that time, so now that one is carrying 10 amps, and now Vs is going to 0, right? But if we just cut that thing immediately, then we will have the same problem. So just after a little while, I mean, this would like to see 10 amp no matter what, and this will start carrying, okay, this will start carrying, let's say 1 amp, okay, and then whenever that starts in conduction, so our output voltage will be 0 again, and it will take 2 amps, 8 amps, 3 amps, 7 amps, whatever, then it will reach to 10 amps again, then this will reach to 0 amps, then it will get close. But from the output voltage level, in this case, it doesn't really matter. I will keep like 0 voltage. I will not have negative voltage at the output, because whenever I want to get negative voltage, that diode will get into the connection and like make it 0. So the main thing that you need to remember, without let me call that area A. So without any line inductance, if we had an ideal grid, I will have that average voltage, but due to commutation I lost that blue area, so my output voltage average is now reduced. So output voltage is reduced. So commutation is always a factor, trying to reduce my output voltage. So let's see the the voltage case. I mean, this is maybe better than my drawings. So this is my VD voltage going like that. We already discussed that. This is what you see at the inductor voltage. Whenever there is a difference between Vs and the output voltage during the commutation time, you see that portion at the VL. But whenever commutation is finished and the current is carried by one of the diodes, so basically the inductor voltage will be 0. So this will be 0, and again there will be some negative voltage through that time. We don't see that time. And this is the waveform. This is the waveform that you see in the IS, source current. So with no inductance, you were expecting to have some square waveform, but now this square wave is kind of softened, rounded. Okay, so you have not sharp edges, but you have that kind of increase, and during reduction you have that kind of reduction. So remember that source current is same with the inductor current. So VL is L di over dt, and you can take the derivative of that waveform, and it is not infinite anywhere. So cool. How to calculate the commutation period? So how can I calculate the commutation period? So let's go back, and basically let's call this area U. Okay, and I would like to calculate two things. One of them is how long that commutation period takes, and what is the area lost. So because without the commutation I was going to have all the area under that sign, but with the commutation I lost that area and I will have only that part. So I would like to calculate both of those things, and remember that VD voltage is square root 2 Vs times sine omega t, right? So let me write my square root 2 Vs sine omega t, and that is the same thing as during commutation. Remember, during commutation that one is on, so that is 0 volts. That is 0 volts, and basically my inductor voltage is the same as my source voltage. So I am writing the inductor voltage, which is here is VL, and that one is equal to Ls times dis over dt. Alright, and this is for during commutation. And I want to integrate that part, and I have omega here, and I have a derivative with respect to theta t here. So from calculus you can remember that trick. I can multiply with omega here, I will have dis, and I will have the omega t here. So that's just a mathematical trick, to use these functions, because this is in the form of omega t, this is t. Similarly, you can get rid of omega t here, it is the same. So that thing is equal to square root 2 Vs times sine omega t. So let's take that one to here. I will have square root 2 Vs times sine omega t times d omega t is equal to omega ls dis. So I need to take integral of both parts, integrate both parts, and if I integrate it, let's say from 0 to u, so u is the end of the commutation, so I'm trying to get that area, so Vs times sine omega t d omega t, and that one is equal. So how can I calculate? I mean, these two are constants. I can take them outside, and I will integrate it as a function of the current. And if I just go back, so So basically my inductor current is increasing from 0 to I, okay, ID, let's say. So, and that change, that integral is basically from 0 to ID, and that part will be equal to obviously omega ls times ID. And what about that thing? So square root 2 Vs sine omega t from 0 to u. If you go back and look at that red area carefully, because this was original the same waveform, is going up, and this is the same red area here. So this is, that expression 0 to u square root 2 sine omega t integral is basically my area. So I can write it like the a u is equal to that one. So that area is voltage radian seconds area lost due to commutation. So basically that area is equal to omega ls ID. So go back, that area is equal to omega ls ID. That is the area lost. So I will also show how to calculate the U, but for now, if I want to calculate the average voltage, so that is the area lost due to commutation. So without commutation, remember, what we have is we had to integrate all that area and divide it by 2p. So basically we had average voltage is equal to, I have 2 square root 2 Vs RMS, but I have only one of those area, 2 over 2p area. So this is square root 2 divided by p Vs, so this is 0.45 Vs. Okay, so this was without commutation, and with commutation, yes, that is the area. So V average will be my 0.45 Vs minus the average voltage reduction. So I have to divide, this is, remember, this is not voltages, this is area voltage and seconds, or voltage radian seconds. I want to get a unit of voltages, so I need to divide that reduction over one period. I have to divide it over 2p. So that reduction, omega ls ID divided by 2p, is my average voltage with commutation. Again, I think you can get derivation yourself, and you can also get help from the book, and you will understand that thing. And from, apart from the derivation, it is more important to understand that one. So commutation actually reduces our voltage. There's a negative here, it reduces our voltage, and commutation gets worse if you increase your frequency. And most of the time, if it is grid connected, it is 50 Hz, but maybe you are using a special AC supply, then it can get worse. And again, the inductance make it worse. Actually, you can think omega ls like the impedance, and as the impedance gets larger, it will affect worse. And the commutation also gets a bigger problem if the current gets larger and larger. Maybe it is not a problem for a 10 amp rectifier, but if you are designing a 1000 amps rectifier, then it will be a more problematic case. So how can we calculate the period U? Let me try to calculate it here. So what I know is that area, and I know the current goes from 0 to ID. So let's take that integral. So from 0 to 2 square root 2 vs sine omega t, it is basically square root 2 vs, and the integral of sine is minus cosine omega t from 0 to u, right? This is just multiplication, and I can write that one as square root 2 vs, and it is minus cosine u, and for that one minus 1, so it is like 1 minus cosine u. Okay, and what is that thing equal to? That thing is equal to omega ls I d. So I'm just integrating that equation. So you can write the cosine us 1 minus omega ls id, and divided by square root 2 vs. Okay. And you can calculate the cosine, then you can calculate what is the value of u, and you can double check that one. If ls is 0, that will be 0, so cosine u is equal to 1, that means u is equal to 0, and as that term gets bigger, that u term gets larger and larger. And again, we have from the perspective of time, as omega increases, our commutation time increases. As ls increases, our commutation time increases. Same with the current. But if you are connecting your single phase rectifier to a higher voltage, if Vs increases, the period wise you will have a shorter amount of commutation period. But at the voltage level, actually it is not related to Vs. We have Vs here, but we don't have any Vs term here, so the reduction value doesn't depend on the value, but it only depends on the omega ls and id. So let me, this is the same calculations in larger formats. So let's do a quick review. So ls and id increases the commutation time, and Vs reduces the commutation time. And in our calculations, so don't forget to divide the area over 2p as well, like we did for the average voltage, because again the unit for that one is voltage times seconds or radian seconds, and this is volts. Okay, you can always double check like that, and voltage or volt time radians. So I am dividing it by radians in order to get voltage. I am trying to get the average voltage reduction, and you can write the reduction, just that term, omega ls id divided by 2p, is how much your output voltage reduces. So again, it is not an easy concept, but if you just try to derive it yourself, I think it will be easier to understand. And let's talk how would it be with a single phase rectifier. So here we have the same thing. So for example, once our output voltage is larger than 0, so basically D1 and D2 are in conduction. So from D1, D2 are on, and I would like to pass to D3 and D4 are on. So again, without commutation, the waveform I would see in the source side will be ID to minus ID with sharp edges, and again that implies if we have some inductance over here, VL is equal L di over dt, and that implies infinite volts. So it will not be the case. So I think you can get the insight that during some commutation period, both and that period, so there will be some kind of I will show the figures, but you can say there will be some smoothing thing will happen in the source side current. So again, it will be the same idea. I'm not repeating it here over and over again. So during commutation, let me clean that part. So, and commutation, remember, it's also called the overlapping period. Overlapping period. So during overlapping, both D1 and D2 will be on conduction. So let's say again for simplicity that is 10 amps, and these were carrying 10 amps, and they cannot go from 10 amp to 0 amp, and these were not on conduction, so they cannot go from 0 to 10 amp immediately. Okay, it will take some time. So during that time, so for some particular amount of time, that will carry 9 amp, and that will carry 1 amp. Okay, that will carry 9 amp, and that will carry 1 amp. Okay, and basically you can say that loop is still getting 10 amp. Okay, and that loop here, you can say 1 amp is coming from here, so that is now reduced to 8 amp. I mean, this is consistent. 9 amps coming from here, 1 amp is going there, so that is 8 amp as well. But what about the output voltage? What about the output voltage? If this is our reference voltage, 0 voltage, so that D2 is conducting during overlapping period, and D2 that is also conducting. So basically during overlapping period, VD will be 0 again. Okay, VD will be 0 again. And if you think about that thing, if you are convinced about that voltage, and this will be the waveform, I will get without no commutation. But now commutation happens twice, both from positive to negative and negative to positive regions. So I will have some 0 volts for some time. Okay, then my output voltage will increase sharply. Then during that period, I cannot go to negative because of the diodes, and I will have another jump here. So there are two important parts. So first of all, AU, the area lost, is not happening once, but it is happening twice. So I'm just having an area lost due to commutation here, and also an area lost in that case. And secondly, from the previous example, I will do the mathematical calculations. This is not from 0 to ID, but it is from minus ID to ID. Okay, so the current change compared to previous one, it was just on and off. It's like a half-wave rectifier. In this case, the source current goes from minus ID to ID, so that will have an increasing effect on the commutation period. So let's try to calculate the output voltage. So let me write the area under that curve. Okay, so that area is the same as the previous one, so 0 to U, and our waveform is same square root to Vs times sine omega t, okay, times d omega t. I am using the same trick, I'm not writing it again, so please refer to other one. Omega ls, okay, so in the previous one it was is and dis, and I was writing from 0 to IS, but in this case I'm going from minus ID to ID. So it will be minus ID to ID. Alright. So the only difference is here. So again, this is the area I would like to calculate. And what is minus ID to ID DIS? So it is basically 2ID. So that is why I have 2 omega ls ID. Twice the value with the previous case. Okay, it is 2 omega ls ID. If you would like to calculate the commutation period, you can write that thing similar to the other one. So that is equal to square root 2 Vs 1 minus cosine u. Okay, that is equal to 2 omega ls id, and you can write cosine u as 1 minus 2 omega ls id divided by square root 2 vd. Sorry, vd vs. Yes. So now commutation period, because we are having from minus id to id, it actually gets longer even if you have the same things with the previous ones. So because of that effect, you will have a longer commutation time. What about the average voltage? So average voltage in the previous case, remember, it was 2 square root 2 Vs is over the area under that curve, and I have 2 of those things because it is a full wave rectifier and it is divided by 2p, and it is basically 0.9 Vs. And I think in the previous video I made an error. So if you multiply, if it is a 230 volt supply, you can multiply that one by 290, and you get for 230 volts RMS supply, V average VDC would be 207 volts. Okay, anyway, so this is 0.9 Vs. This is of course no commutation. So what happens with commutation? Okay, so I have that area and that area with without commutation, and I am losing that area not once but twice here. So I need to I need to subtract my average voltage is 0.9 Vs times 2 times AU divided by 2P, and actually I can write it like that. I know the AU is that value, so it is 0.Vs minus omega ls id divided by p. So 2, there's another 2 here, so that one cancels. 2 omega ls id divided by p. Okay, so I had with the full bridge rectifier, basically I have a increase in reduction, so I will have less voltage because that phenomenon happening not once but twice in a full bridge. So I think this summarizes. This is the voltage value without commutation, and this is the reduction due to commutation. Okay.